Hello and welcome back to Unit 10. In this second part of Unit 10, we are going to be looking at collisions in two dimensions. To start this investigation, we're going to begin by looking at the PhET simulation again. Here it is. This time, instead of looking at one-dimensional, we're going to go into Explore 2D. Now, I'm going to make a couple of changes. I've actually already made a couple of changes on this. I've clicked the More Data button so you can see everything. I'm also going to turn off the reflecting border and turn on, so you can see the energy value. Also, at the moment, we're looking at an elastic collision. So let's reset. Right now, we see that the total momentum in the x direction equals 3.5. The total momentum in the y direction is 1 kilogram meter per second. The total energy is 5.25 joules. Now, I stopped it immediately because otherwise things change. Even though I turned off the reflecting border, I don't want to risk it. After the collision, we see kinetic energy is still 5.25 joules, consistent with it being an elastic collision. If you add up the total x momenta, it still adds up to the same number. And the y is still 1. Return, I believe this was 3.5 of what that looks like it adds up to. Yes, indeed it is. If we change the elasticity, we can get a very different looking collision. Again, but x still adds up to 3.5, y still adds up to 1. Kinetic energy is no longer conserved, but we wouldn't expect it to be since this is an inelastic collision. And if we go to as perfectly inelastic as we can get in this this simulation, and oh dear, it won't let me reset. Well, we'll just let's see. If we do something like this, they should hit. Oh, I missed. So here is our perfectly inelastic collision. We still add up in x to 3.5 and in y to 1. But we have things going in both the x and y directions. So we have to work with both the x and y directions. As before, elastic collisions conserve both energy and momentum. Inelastic collisions conserve only momentum, and perfectly inelastic collisions result in the largest possible change in energy. Let's consider the first of 3 examples that we're going to work. Here we have a 4 kilogram ball moving at 3 meters per second to the right, and it collides and sticks to a ball that was initially moving at 2 meters per second upward. We're told the horizontal component of the final velocity. We want to know what the mass of the second ball is and what the vertical component of the final velocity is. As always, when working conservation of momentum problems, I like to draw pictures. So before the collision, we have our 4 kilogram ball moving at 3 meters per second to the right. And we have our unknown ball that was moving at 2 meters per second upward. Now I'm going to define the coordinate system with x to the right and y upward. After the collision, they stick together and they move off together. What we do know is that the x component of the final velocity is 2 meters per second. We do not know the y component there. We can now look at the initial momentum. It will be the 4 kilogram object moving at 3 meters per second in the i-hat direction, plus the object of unknown mass moving at 2 meters per second in the positive j direction. I can simplify just a little bit here. To have my initial momentum. After the collision, the two objects stick together. So the combined mass would be 4 kilograms plus the unknown m. And then I need to multiply by the velocity, which is 2 meters per second in the x direction, plus an unknown v final y in the y direction. The x direction is the x direction, the y direction is the y direction, and they don't cross. So I can separate this p initial equals p final can become two separate equations, one in x and one in y. In the x direction, initially, I had a momentum of 12 kilogram meters per second. And afterwards, I have 8 kilogram meters per second plus 2 meters per second times m. If you look, all I've done is I've taken and multiplied this in times the x term. This equation allows me to solve for m. So I get 2 meters per second times the unknown mass equals 4 kilogram meters per second, or that the unknown mass is 2 kilograms. In the y direction, initially I had 2 meters per second times the unknown mass, and that had to equal the 4 kilograms plus m times my unknown v final y. Removing the parentheses, actually I don't want to remove the parentheses. What I want to do is plug in the unknown mass. So 4 kilograms plus 2 kilograms v final y. That's 6 kilograms times v final y equals 2 meters per second. And I forgot to plug in the unknown mass here, so we're just going to fix this all up. 2 kilograms. So that's 4 kilogram meters per second. Or in other words, v final y is 2/3 meters per second. Using the x direction, I was able to find the mass. Using the y direction, I was able to find the final vertical velocity. Here is another inelastic collision. We have a 1 kilogram ball moving at 2 meters per second to the right, colliding with a 0.5 kilogram ball moving at 3 meters per second to the right and 2 meters per second upward. We're given the final velocity of the 1 kilogram ball, and we want to find the final velocity of the 0.5 kilogram ball. As before, I'm going to draw a picture. So here's my 1 kilogram ball moving at 2 meters per second this way. And I have my 0.5, small, but I can get it in there, moving upward. And I'm going to call this not final, oh my goodness, wrong letter, V initial B. And if I use a standard X, Y coordinate, I can say V initial B is going to equal 3 meters per second in the X direction plus 2 meters per second in the Y direction. After the collision, the 1 kilogram ball is moving off at an angle. I'm going to call this V final A. And I can write that V final A equals 2.11 meters per second I hat plus 0.94 meters per second j hat, because that's given in the problem. The 0.5 is also moving at an angle, and I'm just going to call that V final B, and that's what we want to find. Instead of looking at the initial momentum altogether, I'm going to look at the x components and the y components separate from each other. In the x direction, I have the 1 kilogram ball moving at 2 meters per second, plus I have the 0.5 kilogram ball moving at 3 meters per second. That gives a total x momentum initially of 3.5 kilogram meters per second. In the y direction, the 1 kilogram ball is not moving. The 0.5 is moving at 2 meters per second, giving me an initial momentum in the y direction of 1 kilogram meter per second. After the collision, in the x direction, I have the 1 kilogram ball moving at 2.11 meter per second, plus the 0.5 kilogram ball moving at an unknown velocity. In the y direction, I have the 1 kilogram ball moving at 0.94 meters per second, plus the 0.5 kilogram ball moving at an unknown y component velocity. I can now equate the initial x momentum to the final y momentum. Oh, let's make that initial x to a final x, shall we? Does not make sense otherwise. Initially in x, I had a momentum of 3.5 kilogram meters per second, and that has to equal, again, 1 kilogram times 2.11 meters per second, plus 0.5 kilograms times v final b in the x direction. 3.5 minus 1 times 2.11 works out to be 1.39. This allows me to solve for the x component of the final velocity of the 0.5 kilogram ball to equal 2.78 meters per second. In the y direction, I can do very similar. 1 kilogram meter per second equals 1 kilogram times 0.94 meters per second plus 0.5 kilogram v final dy. Taking 1 minus 0.94 works out to be 0.06 kilogram meters per second. And now I can solve for v final by equaling 0.12 meters per second. For the last example, we're going to work an elastic collision. Now, remember in Unit 9, I derived a formula that looked like this. This formula is great for one-dimensional collisions that are elastic. For two-dimensional collisions or multi-dimensional collisions that are elastic, this formula does not work. So do not attempt to use it. It will fail you. The setup for this problem is identical to the last problem. We have the 1 kilogram ball moving at 2 meters per second to the right, colliding, in this case, elastically with the half kilogram ball that's moving at 3 meters per second to the right and 2 meters per second upward afterwards. I'd give you the final velocity components, again, of the 1 kilogram ball, and again, I ask for the final velocity of the half kilogram ball. The setup is the same, but we'll redraw it because we can. The initial B equals 3 meters per second I hat plus 2 meters per second J, using again a standard XY coordinate system. Afterward, we have the 1 kilogram moving off at V final A, and the half moving off at V final B. We don't know what directions those are actually in. Well, for the V final A we do, that's given in the problem, but for B we don't, so I just drew arrows. This is going to be 2.16 meters per second in the I hat direction. And I swear I fixed this. This should be upward. Because it doesn't make sense for it to be moving at 2.16 to the right and then 1.39 to the left. It doesn't make sense. As I said, really thought I'd fix that. Okay. Because the setup is the same, I'm just going to write down the answer here, that the x component of the initial momentum was 3.5 kilogram meters per second. And the y component of the initial momentum is going to be 1 kilogram meter per second. Afterwards, in x, we're going to have the 1 kilogram object moving at 2.16 meters per second, plus the half kilogram object moving at v final dx. And in the y direction, the 1 kilogram object is moving at 1.39 meters per second, plus the half kilogram object moving at our unknown v final dy. As before, we let initial in x equal final in x, 3.5 kilogram meters per second equals 2.16 kilogram meters per second times, let's try that again. 1 kilogram times 2.16 meters per second plus a half a kilogram times v final dx. That allows me to solve for v final dx equaling 2.68 meters per second. In y, I can again let initial equal final. So I have 1 kilogram meter per second equals 1 kilogram times, 1.39 meters per second plus a half a kilogram times v final dy. And I can solve for v final dy equaling negative 0.78 meters per second. So object B goes from moving up and to the right to moving down and to the right. Pretty interesting. I am going to point out that we use the results of the 3 examples in this part again in part 5 of this unit.